Yeah, so I'm going to talk about online condensing via random walks. So first, we'll just talk about random walks as we know them. So we know that if you do a random walk on some high quality graph like an expander, the walk will mix well if you use uniform and independent steps for each instruction of the random walk. So you could start possibly at some arbitrary start node, say this one over here, and you just pick a uniform random neighbor of your node to move to next, and then another independent uniform random neighbor to move to next, and again and again and again. And you get something, you can say something about the vertex distribution of this random walk. So one question you could ask is, suppose that these steps came from random variables x1 through xt that are not necessarily all uniform and independent, so they're some sort of weak source. And the question you could ask is, can these random walks still mix? Can we still say something about the quality of the distribution of the vertices after, say, t steps, right? So this is the question: can the random walk still mix after, even if the instructions are not all uniform and independent? And naturally, the question is, why should we care whether that's true or not? And the reason that we're thinking of it is for something called condensing. What we want is that the vertex distribution is an improvement in some sense over the instruction distribution. Right? So you could think maybe the instructions come from some large space in 0, 1 to the n, the entire sequence of instructions, but they only come from some very small subset of possible outcomes for the instructions. And you want to say that even so, even if we run a random walk with this small weak source, you'll end up with a vertex distribution that's maybe almost the entire graph. It's close to uniform or has very high entropy relative to the total number of nodes in the graph. Right. So we're mainly focusing on online condensing here. What do we mean by online condensing? So a natural model of sort of the sources of randomness that you might see is that you might have a stream of symbols coming at you one at a time, x1 through xt. Maybe they're all some constant size, and you want to process these symbols as they come because maybe you don't have enough memory to store all of them and process them all at once. And so that means that the question of whether random walks can still mix when these instructions are not all uniform and independent is sort of similar to the question, or related to the question of whether there's interesting types of distributions for which some online condensing is possible. Right. So I'll talk about a little bit more formally about what online condensing means. So we'll say that a condenser, which takes as input a sequence of instructions and possibly some auxiliary input y, which is a seed, is just a function which starts in some form like this. You initialize some initial state s0, and you repeatedly update this state by taking as input the next instruction or the next symbol in your sequence, xi, and updating your state to that according to some update function. And the hope is that you would say that the final state, which lives maybe in some 0, 1 to the m, is close to having some min entropy k for k that's close to m. So the distribution of the final state is very close to uniform, and where m is sort of close to the original entropy of x. So you're sort of getting as much randomness as you deserve out of this source, right? So the point here is that random walks are sort of natural online condensers for sort of the obvious reason. So let's say you have your sequence of symbols that are coming at you. Each one is in some lives in some alphabet D, and the condenser, you could say, is something like this. The initial state is just some initial arbitrary vertex in some D regular graph, and you just repeatedly take a step in the graph with every instruction. So this is sort of motivates the question of why we should care about whether a random walk can still mix, when the instructions are not all uniform and independent. So in general, it's the case that you can't hope to have any mixing with such weak sources. So if you consider any graph, you can think of some sequence of random variables for which the graph doesn't mix. The one obvious example you could think of is maybe x1, x3, 5, every odd x is a uniform and independent step, but every even step is completely correlated with it and tells you just to take the instruction that takes you right back to where you started. So in this case, you could have a huge graph and some arbitrary start node, but the random walk won't ever go anywhere beyond, say, the direct neighbor, the immediate neighborhood of the start vertex. So this doesn't mix at all. And we should deserve to have a lot of for this to mix, or in some sense, we deserve to have. There's a lot of randomness in this source. It has an entropy rate of 1/2 because every other sequence instruction is uniform and independent, but we can't get anything out of it when we do a random walk. So we're hoping that maybe with some additional structure, some definitions on X, mixing is still possible. So here I'll talk about some of the definitions that we're considering. So obviously, as the most basic part, there's the total uniform distribution. It might be easy to think of this as a deregular tree of depth T for the purposes of this talk. It's not anything really, there's nothing complicated about this. I'm just saying, you could think you start with a root node, and the first symbol reveals where to move among D children, and then the second one tells you where to move among the next one, and so on. And sort of weaker version of this, which are called Shor-Goldreich sources or CG sources. You can think of this as sort of a D to the delta for some small delta regular subtree of this, this original tree graph that we thought of. And just for convenience, because it's annoying, we'll say that all the leaves of this subtree have the same depth. So you could take this original tree, and you could think maybe at every layer, I'm only allowed to choose a small subset of children as my actual children. And I want to say something like, So another way to say this is that there's always some entropy in the next instruction x sub I, regardless of the outcome of the previous xi's, of x1 through xi, right? So this is what's called the CG source. And so classic results will say, for the first one, when everything's completely uniform, if you have a random walk on an expander, this will mix well. In a previous work by us, meaning Donna, Dean, and David, and me, we showed that random walks using CG sources, so when there's only a small subset of choices for every neighbor, we can still have a random walk mix well given sufficiently good expanders. And so now we want to talk about what's the new notion that we can sort of generalize to and say something about, right? So it's fairly strong to say, for example, in a CG source, that at every node in the tree, for example, that you have to have a lot of children, or you have to have a lot of entropy, regardless of what the previous symbols were. So we're going to introduce sort of the idea of an error. And what we mean by a CG source with errors is that maybe there's an error if xi is predictable given some particular outcome of the previous symbols, x1 through xi minus 1. Or in other words, maybe the conditional distribution of xi doesn't have any entropy conditioned on some specific outcome of the prefix. Okay. So in some sense, you can think of this as saying the subtree is no longer regular. Some nodes might not have many children. So here's sort of an illustrative example. Maybe in the first symbol, you could still have many choices for a child. And then for some of those choices of the child, maybe the next distribution is very predictable, or maybe they're completely deterministic. So maybe all the probability weight is on one specific child, so there's only one possible child for the next one. And maybe for some other outcomes of this, you could have still many children. There could be maybe coordinates where the entirety of possible outcomes, regardless of the outcomes of the previous symbols, the next step is completely deterministic. And maybe for some other steps, there's as many choices as you want for the next step. Maybe there's high entropy regardless of the outcome of the previous ones. Right. So we're not going to assume really any structure other than the fact that the number of errors, quote unquote, is limited. And what we're going to do is define specifically what we mean by this for our model. So this is a fairly general model. The way you should think about it is this. So for every possible outcome of the sequence in total, say x1 through xt, you can obviously just break down by the chain rule, like nothing difficult, as the product of the probability that the first symbol is x1 times the probability that the second symbol is x2 time given that the first one is x1 times blah, 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 all the way to the end that the probability that the last symbol is xt given that the previous symbols were whatever they were, right? And for each of these terms in the product, you can ask, was this probability in the product larger than some threshold, which we say is d to the minus delta, or smaller than d to the minus delta? And we're going to say that we hope that most of the time there's many terms in this product that have a small probability. So is in some sense a good step or has a lot of entropy. So right, we want to say that for a typical outcome, not many of these symbols not many of these products in the term have too high of a probability. So specifically, we're going to say that a delta comma rho unpredictable source just means that the expected fraction, where the expectation is taken over a random sample from the sequence of high probability terms. So the expected fraction of high probability terms, which means above some threshold, is at most rho for some small constant rho, right? And so this is a definition that's fairly general. It captures all of the previously considered generalizations of CG sources. And it's actually true that this is equivalent to just general weak sources in some regime of parameters. So if you have some source of randomness x that has min entropy, say 1 minus rho n, then it turns out this is actually an unpredictable source of this form, meaning that there's some, it's essentially a CG source with what we would say is two rho fraction of errors in some sense. Right? So what we can show is that random walks can still mix even with this general notion of unpredictable sources. So here's what we can say. Suppose that you have some sufficiently good lossless expander on 2 to the m vertices. I won't exactly go into the details now of what lossless means, but say some sufficiently good expander on some number of vertices. What we can show is that if you use a random walk, if you use this unpredictable source for any constant delta and constant rho, both of them can be small, close to 1, then if you use this as a set of instructions for a random walk, the vertex distribution of the random walk, if you pick a random stopping time in the random walk, will be rho close to an m minus a constant source. So what this means is essentially this distribution will be essentially uniform. It's only missing a couple bits of entropy in it. If you don't want to use a random stopping time, what we can show is that the vertex distribution of the final step after t steps, right, is rho close to a 1 minus rho times m source. So here we're not losing only a constant number of bits. We're losing a linear number of bits, but we're still able to say essentially, for example, if delta is very small, that this is an improvement over the instruction distribution. Okay. So the way we have to prove this, it turns out, is we need to give an alternative analysis of standard analyses of random walks. So to talk about that, we'll talk about what is the standard approach to random walks. The standard approach is you consider the vertex distribution at every step of the random walk, which is some vector of 2 to the m entries, which denotes the probability distribution. And you argue that at every step, sort of the norm for some definition of norm that you want decreases by some, say, constant factor at every step. So you look at the I+1 vertex distribution, and you can say that it's 0.1 times the previous vertex distribution's norm, right? And in the classic results, you can show that spectral analysis, if you have a spectral expander, then if you have uniform and independent random steps, this is true. The vertex distribution norm decreases at every step. And without some challenge, in a previous work, we showed that this is also true for CG sources for certain types of expanders. And very roughly, this is useful for us because if the norm is, say, smaller than 2 to the minus k, then that means that the vertex distribution is close to a k source. It has k bits of entropy. So if k gets really large, if you can get the norm very small, then that means that you have a lot of entropy in your distribution. Right? So we should ask, can we do the same sort of analysis for when we have unpredictable sources? And the point is that we can't. So remember, what we're looking at is this product from the chain rule, and we're asking how many of these terms in the product typically are greater than some threshold or smaller than some threshold. And what we can see is that the norm analysis will necessarily fail in this type of scenario. And the counterexample is pretty simple. You can think, say, with some constant probability rho, the distribution sequence, the outcome of the distribution is some constant path or some specific preset path, say the all zero string. And otherwise, it would be completely uniform. And what this means is basically that there is this specific path, which, for example, that comes from the all zero string, where every vertex on this path has a probability at least a constant rho of occurring in. And what this means is that at every step of the distribution, you're never going to have a norm that goes below this constant rho, and you're not going to be able to make the conclusion about the entropy from this. So here is what our approach is for giving an alternative analysis, given that we can't exactly do it the standard way, is we're not going to argue about the quality of the vertex distribution at every step. We're not going to say something about the norm. We're going to argue something else. We're going to say that if you look at a typical outcome of the instructions, for every step I, that when you take a random walk with this outcome, the vertex you reach from this distribution, using x1 through xi, the probability weight of that vertex, which would include all other possible paths that could have reached that vertex given whatever your distribution is still approximately the original probability that it occurred. Right? So essentially what we're saying is that we're going to argue that the walk should approximately preserve the original instruction probabilities, the probability of x1 through xi at every step. And this should tell us something that, but this should allow us to conclude that the vertex distribution is good, of high quality. So this is the goal. We want to show that the walk approximately preserves these probabilities. And one simple observation is that this is obviously true when you're just walking on the deregular tree that represents the entire sequence, because in this sense, in this scenario, there's absolutely no collisions. All the probabilities, when you reach any node is exactly what it originally was. So you could have your original deregular tree that considers all possible sequences from D to the T, and you can think instead, whatever my distribution is, the probabilities at every step, if you're just walking on this tree, is exactly what they should be. So this is already true in the case of just a tree. And so what we show is essentially that lossless expanders can be thought of in some sense as trees. What do we mean by that? So you could think, for example, there's some arbitrary start vertex V naught, and then you can look at the next layer, which is the neighborhood of V naught, and then the next layer, which is the neighborhood of V naught, and so on and so forth. And a lossless expander essentially tells us that when you go from a neighborhood, from a set to its neighbor, if you go from a set to its neighborhood, almost every single edge goes to a unique neighbor. So almost every single edge goes to somewhere where there's no collisions. There's no other edge leading to it. So there is some small like fraction of collisions between edges, but overall, there's no collisions at all. And so what this essentially tells us is that typically for most outcomes of your instruction sequence, there's not many collisions throughout its walk. And so it necessarily means that the probabilities are roughly preserved, which is what we want. And so what this tells us, this is essentially the observation that lets us prove our mixing result without going through a norm analysis or talking about how the vertex distribution evolves at every step. Right, so that's all I have to say.